So wait. Great. So this talk is about reusing compiled code in the context of a modern dynamic compiler. The motivation for this work is VM warmup. When an application starts, its execution speed is usually slower at the beginning, and early in its lifetime, the VM collects execution profiles and compiles the hottest methods. And once compiled code for the most performance-sensitive methods is available, the application usually speeds up. So we call this the warm-up phase, and it's a problem because it is wasteful, it wastes hardware capacity, and it makes the application slower to respond. So in the Java ecosystem, there is a lot of ongoing work to improve warm-up, and in our work, we focus on improving VM warm-up by reusing compilation results from previous runs of the same application on the same VM version. So where our work should ultimately lead to in the future is we want to achieve a setup like this. So we want to build a remote JIT compilation server that can compile code on behalf of remote client VMs, and then it returns the compiled machine code to these clients. The benefit of this is that the compilation server can cache the compiled code, or more generally some compilation results, reuse them for future clients, and these compilations from the cache, they should be faster than compiling from scratch, which reduces the compilation latency, and it should improve the warm-up situation. Now, the challenge with a setup like this is that the compiled machine code is usually not easily reusable. So the problem is that the dynamic compiler specializes the machine code to the state of the running VM instance. So this is often what we want because it usually improves performance, but it also hinders the reusability of that code in another VM instance. So to understand this problem, consider the code on the slide. So we have some method do work that performs some logging based on the value of a static final field. And then it performs the actual work. So how would a performant dynamic compiler optimize this? So of course the optimizations, they happen at the IR level, but for the purpose of the presentation, I showed them as source code. So first, the log level field is declared static final. So in Java, once it has a non-null value, the compiler can load that field value during compilation and fold the load. So suppose that the value of the field is the string none, so it can replace the field load with the actual constant. And now in the code, we can clearly see that the branch condition evaluates to false, so the compiler can remove all the logging code. And suppose now that we store this in the compilation cache. And the problem with this is if another client comes in the future, then it tries to reuse this compiled code. However, the value of the log level field was computed with a static initializer, and there's no guarantee that the next time we invoke that application that the computed value is the same. So if the value of the log level field changes in the future, in another VM instance and application run, then it would be incorrect to reuse this machine code. It would cause some incorrect behavior. So this is the problem. In general, compiled code is not reusable because the compiler specializes it to the running VM instance, as I already said. And these are the more specific categories. So the first one is about the non-determinism of the runtime environment itself, and the compiler can somehow specialize to this non-determinism. So what I mean by this, for example, in the hotspot JVM, the compiled code can directly reference VM objects. So the addresses of these objects are embedded inside the compiled code. The problem is that the runtime allocates these objects at different addresses every time the VM is invoked. So reusing that code is usually not correct. Similarly, in the hotspot JVM, the vtable layout may change between runs. So this is another source of non-determinism that the compiler specializes to. The second point is about non-determinism in application code itself. So this is similar to the example we have already seen with the static final fields, but generally there is a problem with final fields, and even very innocent-looking application code can suffer from this problem. So suppose that we have an app that stores the current time in a static final field. Now all the code that reads the value of that field, the compiled code will have the current time embedded in itself. So the next time you invoke that application, the time will change, so it would be incorrect to reuse the code from the past runs. Now the third point is about optimizations based on the state of the VM. So as an example, classes in Java have initializers, and when a class is first referenced, the runtime has to invoke that initializer. But there is an optimization in the compiler. If a class is already initialized during compilation, the compiler doesn't need to emit any initialization status checks, which is great for that VM instance. But the next time we rerun the same application and want to reuse that code, then that class may not already be initialized, which would lead to wrong behavior. Lastly, the fourth point is about object references in compiled code. So what I mean by this, the compiled code may reference application objects living on the heap directly. So it may contain their addresses. So when we want to reuse this code, we somehow need to be able to relocate these references so that they point to the heap of the target VM. But this is difficult to do, because how do we find the right objects? Well, objects in Java have identities, so this is not easy at all. I will not go any deeper than this. If you're interested, the paper contains much more details, so I invite you to read the paper. Now, the idea, what do we want to do about this, is we want to reuse the IR instead of the machine code, because the IR is easier to patch and it's also easier to transform, as we'll see. And to make the IR reusable, we will basically defer optimization to a later stage. So to understand this, first consider this simplified view of a compilation pipeline. So we usually start compiling the bytecode, we parse it into an intermediate representation, the compiler applies multiple optimization passes, and finally it emits the machine code. So this is just an illustrative view. Usually there are many more optimization passes. And now we can view it like this. So basically, the individual optimization passes, they apply many transformations, some of which make the IR more specialized to that particular running VM instance, which is often great because it improves performance, but it makes the code non-reusable. So at the beginning, it could be something like folding the read of a static final field. Later in the compilation pipeline, if the IR references some VM objects with a relative address, then this optimization could be something like choosing a specific instruction sequence. So it could maybe select a shorter instruction sequence if that relative address is small enough. So this is a very optimization that is very specific to that particular VM instance. And this is what we actually want to do. So after some specific optimization pass, we cache the IR for later reuse. So we call this the point of reuse. After the point of reuse, basically any VM-specific transformations are allowed. And before the point of reuse, we need to make the IR reusable. So We do one compilation like this where we cache the IR, and the next time we want to compile the same method for another VM instance, we start only from the point of reuse. And we basically apply the rest of the compilation pipeline. And starting from the point of reuse should be much faster than compiling from scratch. And how do we keep the IR usable? Well, the idea is, the high-level idea is that we should move the transformations that specialize the IR to the running VM instance after the point of reuse. So we should not do them before the point of reuse, but hopefully we would be able to perform them after this point of reuse where we're compiling for a specific single VM instance. And we do this by before the point of reuse, we restrict the compiler's access to some VM state, and after the point of reuse, we run an optimization pass that can do many of these transformations. There is the question of where specifically should we cache the IR, where should we place the point of reuse? Well, this depends very much on the concrete compiler implementation, but generally speaking, if we do that at the beginning, then it might be easy to reuse that IR, but we do not save a lot of work because we have to repeat almost the whole compilation pipeline when we want to reuse it. If we save it at the end, then the IR may already be too VM specific and impossible to patch. So to sum up this idea of IR caching and deferred optimization, compiling from the cached IR at the point of reuse should be much quicker than compiling from scratch, which should lower the compilation latency, which should in turn improve warmup. And with deferred optimization, we can cache IR that is less specialized to the running VM instance, but we can still benefit from VM-specific optimizations by applying them after the point of reuse. And the advantage of deferred optimization is also that basically the IR cannot reference arbitrary VM objects, arbitrary application objects living on the heap. It can only reference constant pool objects, so it is much easier to relocate these references. The potential problem with this approach is that by making the reusable IR more general, we also make it bigger, which influences all the subsequent optimization passes. So some optimization opportunities like inlining could be completely lost. And to be able to reuse this IR, we still need to be able to verify the equivalence of class data. So what I mean, the class data that was used to compile the reusable AR should match the class data loaded in the target VM where we want to reuse it. And we would also need to be able to verify all the assumptions made by the compiler during the original compilation. Now for the experiment, we want to find out what is the impact of deferred optimization. So basically, IR caching, implementing IR caching in a production compiler, that's a lot of engineering effort. So instead, we want to just test the feasibility of this idea, and the key question is whether deferred optimization, whether this, what's the quality of that code. So we implemented just deferred optimization for the GraalVM compiler and ran it on the Renaissance benchmark suite. And the implementation works like this. Basically, before the point of reuse, we disable field folding, and all the IR nodes that represent object constants living on the heap, we wrap them in a new kind of IR node that we created for this purpose. Basically, these nodes then become opaque to the compiler, so the compiler cannot specialize to the heap contents during this compilation before the point of reuse. And after the point of reuse, we basically re-enable field folding, unwrap all these IR nodes so that the compiler can start specializing to that particular VM instance. And the results are the following. So this chart shows the slowdown ratios of the GraalVM compiler with deferred optimization compared to the unmodified GraalVM baseline. So starting from the left, the workload Scala STM bench, there's no slowdown. For many workloads, the slowdown is small, and we have one outlier, Ghost Mix, where the slowdown is almost 6x. Basically, deferred optimization can reduce peak performance, but supposing that we can compile from the cache much faster than we could compile from scratch, then this could actually lead to some warm-up curve improvements in some of these workloads. This is because the code compiled by the GraalVM compiler that runs much faster, of an order of magnitude faster than the code compiled by the lower tier compiler. So if we could manage to switch to this code much sooner by reducing the compilation latency a lot, then this could actually improve warm-up. So Ghost Mix is a clear outlier, so what's going on in there? It turns out that deferred optimization doesn't work with a particular code pattern, and this is about method handles. So method handles in Java, they are a low-level mechanism to indirectly invoke methods. And it is designed in a way that when the method handle is a constant and represents a concrete target method, then the compiler can link it with that target method and inline the target method. The problem is that this doesn't work with deferred optimization. So why is that? The problem is that for this code example, at the beginning, we cannot fold the load of the handle field because we disabled field folding. So the handle is not a constant. And then in the inlining phase, well, the receiver of the call is not a constant, so the compiler cannot find the target method, and it cannot inline it. So it doesn't inline it. After the point of reuse, we re-enable field folding. Now the compiler actually folds the load of the handle field, but it is too late for inlining, so it's not inlined, and this is the cause of that huge slowdown in Ghost Mix. Could we fix it? There is an alternative idea that could potentially lead to better peak performance. But there is a trade-off between the complexity of the implementation and performance. The alternative idea is that we would defer only the transformations that are likely to be invalid in future VM instances. So this approach would be more optimistic. But for this to work, we would need to be able to select which transformation should actually be deferred. And we would also need to be able to verify that for all the transformations that were actually performed, so not deferred, whether they are valid in a particular VM instance. And also, now the compiled code could actually reference arbitrary heap objects, so we would need to be able to patch these. So as I said, this could lead to better performance, but there is a trade-off between complexity of the implementation and performance. To conclude, the compiled machine code is usually not reusable because the compiler specializes it to the running VM instance. The idea that we propose is caching the IR instead of the machine code, differing optimization to make the IR reusable, and applying the optimization after the point of reuse so that we can still benefit from the performance improvements of VM-specific optimizations. And finally, deferred optimization may reduce peak performance, but it could potentially improve the warm-up curves for some of these workloads. Thank you for your attention.
What are your thoughts on using this in like a tiered compilation strategy where you use the cached code initially while the other code is being compiled in the background and optimized more aggressively?
Yeah, sure. That could work. Yeah, we didn't try. I think it could potentially work but of course we would really need to be able to compile it much faster than compile it from the cache much faster than it's actually compiled from scratch.
Slightly naive question, like what kind of optimizations that are invalid in the future? And in that case, why you need that optimization?
Okay, so what I mean invalid in the future, so if you have like a static final int, basically field, which has a value 4 in some run, and in another run it has a value 5. So like sometimes for if you take a particular static final field, some of them they have the same value in all the runs, but some of them the value can change. So like ideally, if you could somehow recognize these fields that the value changes and those fields that the value doesn't change, then you could defer only the optimization of those where the value changes. And this is not necessarily limited to fields, but in general.
Are they common in this, like for this type of optimization paths?
I'm not sure what you mean. Sorry.
For those invalid transformation, right? And are they common in this? I'm not expertise in this. I'm just curious.
Okay, so what I mean by the transformations that are invalid is basically that in the original run where the code was compiled, the transformation is just fine because it leverages some state that it got from the VM, that the compiler basically read something from the VM and it was valid to do some transformation. Okay. But in the future, when you rerun the VM, then something in there could be different. Perhaps an address could change. So if you do the same transformations, then that would be invalid.
Okay, thanks.
Sorry, Andrej. Thanks. Just two questions, actually. One, do you have an idea? You showed us peak slowdowns and peak performance, but is there an idea that you can get for actual saving on warm-up for each of these? Yeah, I do not have the actual data prepared, but this actually depends, of course, where we cache the IR, but in GraalVM, the potential savings actually depend on the size of the method. So for small methods, the savings are actually smaller. And for very large methods, the savings could be 10x or more. This is because basically at the beginning, the compilation time, like it scales, basically the complexity is bigger in terms of the size of the IR and nested loops. But after this point, the backend of the GraalVM compiler is usually faster. It's usually faster. Yeah, so the savings, they depend on the size of the compilation unit. The smaller it is, the smaller the savings. But for huge compilation units, they could be substantial.
Okay, thanks. Question number 2, if you've got time, Fred, is so that's on the warm-up, but also there's also a space trade-off here. do you have, so based on where you place the boundary between VM specific and generic optimizations, do you have a sort of graph or some sort of Pareto optimal curve that can show size versus speed up?
No, I do not have this. I mean, in terms of engineering, we do not have much room where is the ideal place to do the caching. So yeah, I do not have this. I mean, but there is usually just one place where it's reasonable depending on the implementation. I mean, and we cannot really move it easily.
Okay, thanks. Just
maybe we have a couple more minutes. I have one more question. So, what are typical warm-up curves for Graal VM? How does that look like, and how does this add or subtract from that?
Yeah. So the benchmarks that we run, right, like Renaissance and Da Capo, and also depends how we define warm-up. But on these benchmarks, some of them it's tens of seconds until it reaches peak performance. Yeah, but it's also difficult to define peak performance. So it tens of seconds for some of them, and for some of them it takes minutes. Usually after 5 minutes, most of the benchmarks that we have, they should be warmed up.
Thanks. So let's thank this.